Hi guys, should I watch this one a bit? Should I rub this one? Hi everyone. As we know, we need 10 viewers for me to start something. We had 12 viewers. That's nice. So I'll just solve some problems, I guess. If you guys like my streams, you guys can try along. Someone gave me some problem already. 2181D. Hi Mohit. You're not second. Sanatan KR. Oh, you're second. I see. Someone else has already suggested me. You should have been quicker. So we have an expert, live solving expert, who's saying, oh, I'm at my friend's home, but I'm staying here itself. I'm staying here. I'm trying to grow my hair back. It's light, bro. Don't fall. I'm not even practicing CB. I'm not much bothered about my rating, right? But I should do it well, just in general, because I'm streaming. I think I should be performing better. Hi, Tom Scott. I don't remember. I remember you, Tom Scott. You were there on one night. You were saying the same thing, I guess, even then. My memory is too. What are these notifications? Yeah, sorry for the notifications. I'll just close these things. And what is Tonit Suzake? Tonit Suzake. Let us make this number theory stream. You guys know what I have done recently. I tried making a YouTube short. I will not do it ever again. I will not do it ever again. What is this? See, I tried doing this one. I tried using cursor to wipe code this one to just show this one that we use the formula to show that, but that's not the proper way. We can show it better using bijection, which is NCR is just choosing two elements from n, and NC n minus r is choosing n minus r. And the simple bijection we know is when you choose these two things, you can see the complement. You can map them uniquely. You can map back uniquely. I mean, you guys should be clear with the basics. Like one is proved like you can map them uniquely. Like it proves one, and each of them has something coming to them. So it's on two. So if it is one or on two, you can say choosing and not choosing is the same. But if you be more formal, you have to see the sets and then you show the bijection and then you say the set size is same. I tried doing this, but I will not do it again because it took me so much time. Instead, I will just do directly writing on some drawing board or iPad, and I will just make some shots rather than trying to do this. It took quite a while on cursor. I should not be doing that. I was bored, so I was doing that. Oh, is that a name? See, guys, we don't have much time. I will go ahead with this first problem that I have seen. The first problem that came here is 2181D. Okay. I haven't solved this problem luckily. Let's try to read the problem. The construction of the doorway for the. Do you guys have any other questions? Maybe I'll raise Q&A and answer later. I can see the chat during Q&A. Yeah, we cannot just say that is what I mean. You have to be more clear is what I was trying to say. Like the video too, guys. The construction of the door. So let's try to read this problem, okay? The construction of the doorway for the nonsense engineering and research convention was delegated to one of the future attendees who decided on a multi layered sliding door design. See guys, what all you have to be trying is what all you have to be trying is nah, I don't want to reach right. What all you have to be trying is trying to simplify things. Problem solving is about trying to simplify things. Problem solving is about not having any fear. Like, you guys should not learn knowledge from problem solving. CP, don't make CP lame. CP is not lame enough. Like, you get some knowledge. CP is good in some way, even though in contests we feel like it's draining or like annoying sometimes, but it's good in terms of like to solve a problem is good, because CP problems doesn't use external knowledge. Everything is self-contained in the problem itself. That's why they give you definitions here. So what you have to learn from CP is to not have much fear, like, because if you are used to competitive programming, definitely if you open some higher rating problem, you will have that fear in the background. Like, you will think maybe I can solve it. You will have the anxiety that maybe I can solve that. It's, you can use CP to overcome those things and you will eventually do better. Like, you can learn things like trying to do what you can do is always the best thing to do, rather than worrying that you don't know what to do. Trying to do what you can do is the best thing to do, like, because if you do what you can do, problems will get solved eventually if you keep doing what you can do. Because you can do so many things if you try, actually, because you can limit the constraints. Maybe you can think of what happens if k equals to 2, what happens if k equals to 3, whatever the parameters are. Because if you actually try optimistically, there will be so many things that can be done to approach solution. But if you think it might be out of my reach, you cannot do anything. Like, you get stuck. You get stuck even before reading the, like, how am I stuck without reading the problem? I'm talking nonsense, right? uh, who decided on a multi-layered slide design? So let's read the problem again. Well, so what was this? Was delegated to one of the future attendees who decided on a multi-layered sliding door design. So we have multi-layer sliding door design. So these are the doors, I guess. There are multiple layers. Each layer can be described as a horizontal interval bounded by two solid walls on the left and right, containing a number of sliding doors on fixed lengths. So you have to understand the problem. Two, each layer can be described as a horizontal interval bounded by solid walls on the left and right. So each layer is bounded by solid walls on left and right, containing a number of sliding doors of fixed lengths. So each layer contains a number of sliding doors of fixed lengths. It seems within a layer, each door can move independently to the left or right as long as it does not overlap uh, other doors or the walls. So we have some doors in between. Doors can keep moving, but they cannot overlap. All layers are parallel and stacked vertically. So all layers are packed like this. After construction, the organizers noticed a problem. You guys understood that, right? Like, there is boundaries. There is some boundaries. There are some walls. Maybe I can use. I forgot the name. Forgot that app name. Yeah. You have to open it twice. I should maybe get an iPad. I don't know. We are still at reading the problem. So what they are saying is each layer has some boundaries, and in between there are doors that can move along. Doors can move, but they cannot cross each other. That's what we have seen so far. After construction, the organizers noticed a problem. It is difficult to fully open the door, and since a large number of attendees are expected, they need to create the largest possible opening to allow everyone to pass through freely. So it is difficult to fully open the door. And since a large number of attendees are expected, they need to create the largest possible opening to allow everyone to pass through freely. So let's see what is the opening. The size of the opening is defined as the total length of horizontal interval such that at every point an interval at every point of such interval, and in every layer there is neither a door nor a wall. Your task is to determine the largest possible opening given the door's layout. So it need not be consecutive. The total horizontal intervals such that total length of horizontal intervals. So I think it need not be consecutive. Like, see, when there are more parameters, and you have to just solve the problem always. How many parameters are there, or whatever the problem is. What does how are they defined? The number of sliding doors on that layer, the x coordinates of the walls on that layer. So x1 is this is the first wall. So number of doors, first wall, second wall. The number of sliding doors, first wall, second wall. So what is k? Number of doors is k, and we have x1, x2 likely, and there is a wall at x1 I1 and a wall at x2. At all positions x less than this are blocked by walls. Following k integers li1 up to so on, it just indicates the lengths, because their position need not be given because they are movable, right? They are movable. The length of the sliding doors on that layer given in order from the left most door. So we have these lengths L1, L2 up to so on. Some of these lengths less than or equals to x2 minus x1, so they fit in between. Total number of, you have to see the whole problem also clearly, because many times we miss the problems. From left side to right side we have the lengths. It is guaranteed that uh, total summation of total number of doors is less than or equals to 3000. The size of the largest possible opening that can be achieved by moving the doors on each layer. So you have to think of you have to see, we have to prove, we have to also prove that this is the largest possible opening, right? It's not just trying to think of a procedure. Like, you have to prove that whatever the procedure you're doing is largest possible. It can be limited. Are there any upper bounds or lower, or we have to try for upper bounds too. We should try to think of upper bounds, like, will anything limit? I want to see one thing. If we have two doors here and three doors here, will all these things add up? Let's say you only have one layer, okay, and you have two doors. Will both of these add up to the answer, is what the doubt I have. I have to read the problem clearly for that. Are there people, you guys try to think of the problem along with me. The key is to this problem is to treat each door like an event and do something similar to line sweep. See, the key is, you're given a problem, you have to solve, you have to prove that this is the optimal. Like, it's same, it's applying logic. You need not get something from somewhere to, you need not even do line sweep. Like, you have to just solve the problem logically. And hi Ari, and you have to solve the problem logically, and you have to prove that it is perfect. So it's like a puzzle piece. All problems are like a puzzle piece. Most of the times they can be easy. So try to say what you can say. Are there any upper bounds? Like, let's say you have so many doors, but if one door is having very small length, that limits everything, right? So if one door is like having very small, that itself can limit everything. So now try to think of it. If one door itself is like very small, that itself can limit everything. Now let's try to look at optimal. The ways we have in problem solving is like one of the common ways is looking at optimal, right? let's say somehow let's say somehow this is the opening that you are able to get. These are the L1, O1, O2, O3. We also are fixing the coordinates, because why? We can do anything logically, right? uh, so let's say these are the optimal things that you have. So what does that mean? There is a way that everything above can, for every door above can be moved such that this can be made empty, this can be made empty, this can be made empty, and so on. Okay, so now what can you say? Where have the times gone? So now let's try to apply something greedy. See, how you apply greedy is you don't think of a greedy algorithm. If you think of a greedy algorithm and then you approach the solution, it's due to luck. That's why you may get stuck in some other problem. How to apply greedy is you have to look at optimal and then you have to see, can I do something greedy with the optimal? Like let's say this is optimal. Can I can I move the first door in here? Can I move the first door in here a bit leftward and still maintain the optimality of the solution? That's how you approach to a greedy solution, not by like trying to think of greedily. Okay. Uh, so let's try to see if you can move this a bit leftward. What happens if you are moving? Like you have these things, right? You have these doors. You have these doors. Currently, this one is contained in all the doors. But if you keep moving it leftward, what happens is, so I think we can do something greedy here if you're seeing it. So what happens is, I'm doubting one thing. What if there is a door here and there is a door here? This should not be allowed, right? This is not like an opening. Otherwise, then we can just stack everything. So there should not even be a door in between. So there is neither a door nor a wall. That's the clear question. So this is the optimal. Like you have some intervals, set of intervals. The answer is the sum of all the intervals. It has been told very clearly because at each point of such an interval, when they say such an interval, this is such an interval, this is such an interval, this is such an interval. So let's try to move it a bit greedily. What will happen if you move it a bit greedily? Uh, you cannot move until you encounter some door, right? Until you encounter some door, you can move. So you can say that there is an optimal that starts with one door. Now let's say you can move everything. You can move all these things a bit leftward. You can say you can move all these things a bit leftward. Maybe there is some door before. So what I was trying to say was, if there is no door before, I was trying to say that you can say that there is an optimal, I mean, optimal start would be when you compress everything like this to the left, one of the starts will be some optimal start. That you can say a bit greedily, but that doesn't seem to be giving us much. Let's try to still think like we have this optimal. So let's say this one is possible. How can doors be in the above things? That there can be something in middle which is small and still this can cover this one. I'm not able to solve recently, I guess. You guys can still try, keep trying. See, let's remove the blocked walls. Let's not even think about the blocked walls. Blocked walls comes later. So let's say you have just blocked walls can be equal, right? So you have just layers. Let's try to think how difficult can this problem be. You can move these ones around, you can move these ones around, and what's the maximum doorways that you can form, right? So it's like maximum common intervals, right? If you try to see that, maximum common intervals that can be formed. I don't get it. Why can't you compress them like this? Why can't you compress them like this? If you compress them like this is still an interval without any door, right? This is still an interval without any door. This is still an interval without any door. So how is only taking this one different from taking this one plus this one? How is that different? So I think we can combine doors. But then isn't it too weird to just attach doors completely and then count the lengths? What am I arguing here is like, how is what happened here? See, how can someone call this to be optimal pathway, and let's say there is something else to here, and this to be optimal pathway, and not call this one to be optimal, because even here you can say this is one interval and this is two in second interval, right? So are they just trying to confuse us with the problem? Because this is a valid interval that doesn't pass through any doors or any shit. This is a valid interval and doors are infinitely thin, right? Infinitesimally small, right? Door doesn't have any width, I believe. Do doors have width? I don't think doors have width. We have k, x1, x2, and then 3 and 2 lengths. So this is one door and this is one door. 3 and 2. And what about this? 1, 1, 2. 1, 1, 2. So what's the optimal you can form? They're telling 4 is the optimal. What? I have understood the problem. Fuck. Those are not doors, those are walls. This shit is walls. I thought we can open the door and go through the door. But the problem is you cannot pass through doors. I mean, door is to enter, right? Why do they call it door? Okay, it's movable door. So it moves and then you enter. It doesn't open. It slides, sliding door. Okay, that how the door functions here is, see, I'm taking too long to understand the problem itself. The door is of this type, where it gets attached. Like in Doraemon, we see those type of doors, right? You slide them around. I think Doraemon doors have this design on them. So this is how those doors look like, right? So this is how those doors look like, right? These are movable doors. So those were the doors. I thought like door is to enter, but these doors are not to enter. These doors are to slide away and then you have to enter. Those are those doors. You guys get what I mean? I thought doors will open. Yeah, Japanese house doors. I don't know. I just got to know the problem now. How will it become a cakewalk? So now let's try to think about the problem again. So now this makes sense. You have to move them around and then you have to find a way through and then you have to move there. Right? So now the lengths are not fixed. Okay? We have these two walls, right? Now this maximum of x1 is definitely a limit because this maximum wall, so we can obviously eliminate the two boundaries that we have. maximum on this side and maximum on this side are the boundaries that you can just get, because those are the boundaries, right? You cannot utilize this at all. The walls don't move, only the doors moves. Okay, now you have this clear one, and you have some doors. See, if you can, for remaining things now, if the wall is small and if you can fit a door here, fitting that door here is best, I guess, because if you can fit some doors, I think that's definitely optimal thing to do. Why? If you are not fitting them, they are somewhere here. Just move all of them here. You just have more space, right? You have to argue math. You have to argue logically always. Like, what's the argument? What's the argument to say that you can just what? How many number of doors that fit here? You can just below this. You can just fit them. What's the argument for that? Let's say there is a door or there is a set of doors that can be moved. There is a set of prefix that can be moved here, and let's say some prefix doors which can be entirely moved before this or here, and you have the optimal. Just move them ahead, you will still have the optimal, right? So you can do that greedily, like that's one thing you can say, but the problem is not yet done. Let's say you have done those things too. Okay, let's say you have done all those things. Now you have to think. See, now you have, if you have done all those things, any other door, now you look at any other door. Okay, you have these walls here which you have moved already, because see, we are approaching optimal one by one, like we are approaching optimal one by one. So if these are the walls, now let's say, now if you push any one more door further, because you are very sure that there is an optimal with these things being here, so that's fixed. Now we can try to think about what you can say for this optimal. So you told that all of these things can be pushed forward. Now you have this one. If you push this, it won't completely go, it won't completely enter. Do you get what I mean? This door will not completely enter, and that's true for everything. Okay, for everything, if you try to push this door inside, it won't enter completely. So now what can you say? Is it always optimal to push all doors this side and all those this side and make a way in between? Is that always optimal? Maybe think of that too. Let's just look at the optimal pathway. Maybe that is also true. I'm See, I don't see the problem intuitively at all. I only see them mathematically. That's why I never see them like intuitively. I never use intuition. So even though, I mean, I got to know the problem, correct problem after a while, but if I see that now, we can clearly see, like, let's say this is the optimal pathway. This is the optimal pathway. Like, you have here some optimal path, and then you have here some optimal path or something. You can likely move everything else to the side, because there are some set of doors over here, right? There are some set of doors over here. All the doors over here, all the doors over here, there are some doors over here. Doors are completely contained within, so you can move this part into this side, and you can combine the green. So it's obvious that, because if you see the optimal green pathway, they need not be separated, because if they are separated, you can clearly see that you can move this whatever the doors that are here, you can just move them that side, and you can combine the green. So the problem is quite simple. I haven't seen the problem well. Somehow I was just trying to say something. Maybe I have to learn from this. Maybe I have to learn how to solve better, because I'm not solving recently at all, right? It's not that difficult problem, but see, the problem is you have two walls, you have some doors which can slide, you have to make some green paths in between so that there are no doors at all, and then you want such length. So one thing you can say about optimal, the first thing we said about optimal is, which is quite easy to see, all the green paths can be merged. Means there is an optimal like this. So they have confused us. See, they were asking us to see total length of intervals, but then in optimal there exists an horizontal interval. So this means there exists an horizontal interval such that it's optimal. You need not have multiple intervals to have optimal, because if there are some doors in between, this is completely free. You can just move this set here, and then this length will come here, so you can combine them. So that's one thing that's true. Okay, so now maybe you can brute force, or you can just like, now there can be many solutions. Like you can just try to brute force, uh, I mean, you can try to greedily move few things this side and few things this side based on drawing a line in between or something like that. Let's say you're trying to brute force. Let's say you're trying to brute force the now you know the green line is a green length is a clear width, right? So let's say you're brute forcing this one. How would you do that? So this is one length that you're thinking, you're trying to brute force that. So now you have to find the optimal green that you can form from here, right? How you can do that now? So everything in every row, if something can be moved completely before that, just move it, because you can clearly prove that that staying somewhere here will not increase this, will not make it better. Moving that completely beside, so all the prefix that can be moved completely beside, you have to move that. So now you cannot move anything further, then all these things should try to go as far as possible on this side. That is also clear for us, right? Because if it is being closer, that only affects the value. If it's being as far as possible, that only increases the value. So if you're brute forcing this one, you know the answer. Move everything that can move here this side, and you cannot move anything to here because it won't fit completely. It will obstruct, it will stop the thing here itself, because you are brute forcing the start already. That is not possible. See how brute force, logically we are applying brute force again, because you may think, whoa, maybe if it comes here, that might be the optimal, but you have fixed that this is the start. You are brute forcing, because uh, if this was here, maybe when you are brute forcing from here, that would have been covered. So let's say you're somehow brute forcing this length. If you're somehow brute forcing this length, then moving everything that can be moved forward, okay, moving everything that can be moved forward is good. Moving everything that can be moved forward, let's say if you're brute forcing the start, everything that can be moved forward is start, and everything else should be on left right side. So we have clear lengths possible for each so we have clear lengths that are possible for each of the layers, right? Once you fix that, the problem is done. So do you guys agree that once you fix this one, you can just solve the problem? 1 minute, I'll repeat. I'm not doing binary search, I'm just telling that, see, first thing we got is the green pathway is like that. Now I'm trying to brute force this one. I'm trying to brute force the start of that green pathway. So it's not that complicated if you try to see clearly. Now I'm trying to brute force it by fixing this and try to understand the problem. Okay, if I fix this one, and at each layer, I hope changing colors is a bit easier. At each layer, let me draw again. So I'm trying to fix the right side of this one, okay? Now what happens at each layer? Same logic, if some doors can be moved completely here, moving all such prefixes here is best, because they cannot do much here. Now if you see the next one, for you this should be empty, so you cannot keep it here, because that will destroy this to be non-empty. So what should you do with the remaining doors? You have to push them as much as you can to this side, okay? Then you will get one length for this one, and after you fixing that, you will get such lengths for every layer. The answer is minimum of all such lengths. That's just the answer. So if you are brute forcing this one, you can solve the problem. So in trying to solve the problems, you have to think, You have to see the optimal and then you have to say, can I say something about that? In here, there is a rectangle. So what can you say? You can say this start. Now you can think, if you were given this start, can you solve the problem? That's what brute forcing is, right? Let's say somehow someone told you that this horizontal x is the best optimal x. The horizontal start is the best optimal. Then can you solve the problem? Then can you find what length is possible? You have to think like that. Like if you can see some parameter or something, maybe you can try to think of it. Can I brute force that also? So now if you're trying to brute force such things, what is this one? Optimally moving some of these things to the, pushing some of these things to the leftmost, pushing some of these things to the rightmost, and then you got a layer, right? That layer has, see, this was our idea to approach to a solution. But once we have approached to a solution, we are trying to see the important things in each layer that are being formed. The important things in each layer that are being formed is some prefix moved this side, some suffix moved this side, and then what was the interval that was in between. At each step, you have to see if we can make the solution better. So there are some important layers, right? So for one layer, opening the doors, like trying to push these things, try to push one thing, push everything this side, try to push one thing, try to push everything this side. This will give you different segments that are possible, right? As you push less here, this will be less. As you push more, you will have this one. See, now I'm trying to say, once you brute force this, you can see that there are these greedy pushes, and among all such greedy pushes to the front and start, you will have these layers. Now the answer is maximum of such layers. Okay, now the answer is maximum of such layers. So if you see this thing, if you see those layers that are being formed, like just by pushing first thing here and everything this side, pushing two things and everything this side, if you see those layers, the start will keep increasing because you are pushing more things inside, and this will keep decreasing because you are, so those layers will be moving like this. Okay, so now you have these layers. Now the answer, optimal answer is, you have to choose one layer from each of them, and then you have to see what's the biggest pathway that's there. Maybe you can brute force itself. Let's say you have all these layers, because finding this lens is not difficult, right? Finding this lens is not difficult. Finding this lens is easy. I'm trying to see more about those lens, but finding this lens is easy. Okay, I will stop by 7 o'clock, whatever happens, uh, because I can't be investing my time for my own practice too, not even for you guys. I can't be investing my time for my own practice to have work. Have have to go to, maybe I'll go to gym to a bit after this, but so I think this, let's try to see now, let's try to brute force this one. Okay, so to brute force this one, the value seems 1 1e9, right? You won't brute force 1 to up to so on 1e9. You will try to brute force again, applying the greedy logic a bit. Okay, once you push this once, you have this green thing that has formed, right? You have many such green things. You can move the green boundary, it touches some green boundary, the left side of green boundary, because you're just getting more. So for optimal, you can say optimal will start at one of such green boundaries. All these belong to same layer, but if you see over multiple layers, you can say optimal starts at one of the right of the green boundaries. So now you have only O of k starts. You don't have 1e9 starts. You have O of k starts. If you see all the green layers, and if you brute force on this starting point, then you have only O of k. Okay. So you know the start points. Now for each start point, okay, for each start point, you have these greens, let's say. Okay, you have to see the greens that start before, and then you have to take among all such greens that start before but end later. Okay, you have to take for each layer, among the greens that start before, you have to take the optimal green, which is nothing but the largest green that starts before this would be the optimal green, right? Because we have seen if this is smaller, we'll have smaller green. So you have to find for each layer. So when you're brute forcing this one, for each layer, you have to find the smallest thing, biggest thing that is less than that. And then if you have those values, minimum among them will be the answer. Okay. So what am I doing? I'm brute forcing this. And in each layer, the biggest thing that is before this value, see, I'm brute forcing one of those ends itself. And then I'm telling for each layer, the highest thing will give me the maximum one. Highest thing on this side will give me the maximum one. Okay. And among all such values, we have to find just minimum. Then we will know the optimal length of this side. So we are still brute forcing this one, but to brute force that one, our claim is that brute forcing at starting greens is fine, is good enough. Did anyone understand what I mean by green? Green is nothing but push some doors this side, some doors this side, whatever is formed in between is green. So you have O of number of doors, greens per one layer. Now the optimal answer is if you fix one green start, you can see that it is choosing some green in every layer. And then you can see that the optimal can always start at one of the greens start. So now you have optimal starts which are just O of k. So you're brute forcing again. But see, the problem comes in steps. It may appear too complex, but it comes in steps. So one is forming greens is one step. And once you form greens, green start is an optimal. So now you have to think of what's the best way to move. You have to move from all, you have many optimal positions of green, which are just O of k. Let's try to move in this direction. Let's try to move in the increasing direction of the starts, okay? And you're observing each layer, okay? So for each layer, if you're trying to move from this one, what you have to maintain, let's say this is the current brute forcing green you have. You have to maintain the green that is less than this. You have to maintain the highest green that is less than this. You just have to maintain that. So what can you do? You can just let's say you have all of them in this. Let's say you somehow maintain that. For this, you maintain its biggest value. So if you maintain all of them in a set, just taking minimum among them would give you the optimal length. But how do you maintain these things now? How do you maintain once you are here and then you move forward? You have to, if you have moved forward, this will be gone. This will be gone or not. Something new will come inside. So that will have an better optimal answer. Like if you take its R, that will be more optimal. So when you move forward, there are some more things that are coming into that. And then there are some more R values that you are getting. Okay. But whenever you move forward, you should not go over all the layers. You have to only go to a layer if something comes inside. Okay. If something comes inside, only then you have to go. So let's just put all these greens itself in a big set. And once we move from here to here, we will try to see if some green is falling before. And for this green, what do we maintain? We maintain its L, we maintain its R, we maintain its index, let's say. So now we can just, once we move forward, we can just query all these things to find, okay, this green is coming before now, because you can just query with respect to L, right? You can pop this L out of the set, and then you have this LR. And with respect to I, what do? You will update this value, you will remove this value, and then you update its value to the better R. So it's as simple as that. Do you guys get what I mean here? Like it's like it's brute forcing. That do this problem has nice idea? I don't think it has nice idea. It's about brute forcing. It's about brute forcing in a nice way. So you have some greens. After you set your boundary, you have to say after you fix your boundary, you have to take in each layer. You have to take the largest L that was before that. How do? You pop everything that is before that, and then you update this value to the maximum R. You pop everything from the biggest big set. Once you pop that, you update that value for this R. And once you do that, you want just want the whole maximum. That's it. You just want the whole maximum. So what should be this initial value? So you have L, R, comma, I. If something is fitting completely, then everything is blocked. Then the answer is 0. But so now the problem is done. So all we have to do is, how do you form all of these things? And then you will go over each L, and then you keep removing things before that. See, going over each L is nothing but removing things like this, like this, like this. And then you update. So going over each L is also same as removing things from this set and updating these values and then getting the maximum. It's same as that. But then your L will increase. So let's say in this thing, this was the one removed. So you will have the last removed L. From there you will start maximum L that has been removed. And then you just find these maximum answers. So I was only thinking what should be the initial value, because you have to remove that from that set and then you have to change that value to this R. Right? So let's just make it 0, because you're removing 0 and then you will add something bigger. Right? So that should do it. So what we should do, we have to find all the greens, and then what should we do? We have to keep them in a set. We have to pop one after the other. Once you have popped till here, whatever is the maximum L, and once you have popped for all of them, you will store the maximum R in each of those layers, and then you will get minimum of this set, and then R minus popped L would be the answer. Only difficulty I'm seeing is how do you maintain this initial values, and once you are updating its R, you have to remove this thing and then you have to update. Let's say initially you're setting to 0, all of them are zeros, and once you get one I, you will remove 0 or the current maximum, and then you will add this new R. That will definitely be better R. And how do you maintain this L? Let's say you make it 0 or something. Let's say you start from 0. If there is nothing starting before that, the R will be 0. Because the R is 0, nothing starting before that. That is even correct, because R minus L will become 0. And always 0 minus, as long as this layer is not helping, the value is 0. So 0 is the right value to give. So now how easy can code be? We will form all greens, okay? We can put them in a vector, not even set. We have this L, we have these initial maximums, we can have a set for the maximums, right? We have 6 minutes to code this shit. So I will maintain one array initially set to 0. This will give us max R, let's say. Okay. And what do I find? I will find all the greens that are possible. Or what are all the greens possible? So for each I, this is all I need. So how many greens we will form? We will form k plus 1 greens. So moving everything that side, moving everything this side, right? Why is my Copilot not working today? I don't know if using Copilot is good or not. So now L is x1 plus L of L, like pref L of I till some point, okay? And R is x2 minus sub L of I, right? So this is just that. So we want all the sum. Let's say, let's just form pref of L. Okay. Let's just call it pref. We don't have too many arrays here. Now, let's just say nothing is pushed forward. If nothing is pushed forward, what is that? We have k plus 1 greens. If nothing is pushed forward, what is L? L is x1, comma, everything is pushed forward this side. X2 minus pref of L minus k minus 1. Okay, comma I. We will also store the index where it has been pushed. So now for int, see, we don't use this x1 again. So let's just update that variable because we don't use it again, right? So let's just update that variable. X1 plus equals to L of I, because that shit has been moved forward. It's L of J. We have to be careful in coding a bit. This is right. So now we have the updated X1. You have to move all these things to this side. So what are all these things? What is the length of all these things? You can start with moved x2 and then you can just move, you can do x2 plus 1. That will look cool. So let me just do that. Okay, so I will now literally move one after the other. So now I will literally move this one this side and see what happens. Okay, I literally move this one this side and what happens? What happens if you move this one this side? X1 will increase, but what happens to x2? X2 also will increase by L of J. That's it. Because I don't use those x1, x2 again, I'm just moving them itself. Like, so everything has been moved this side. So x1 and x2 is this. Now that thing came here. So x1 moves, x2 moves. Actually, all of them are of equal lengths then. If something comes, the equal lengths, the gaps are all of equal lengths. Like all the greens in one layer are of equal lengths. What can you say if they're of equal lengths? I don't know. We got a solution. Let's just go ahead with our solution itself. So now what should we do? Sort greens. How this max sort, right, for each layer. I'll maintain a set. Initially it has all zeros. Multi-set. So we hit the time already. Now what do I do? We will keep popping. So we'll keep popping this one. Let's say L equals to 0. Okay? We keep popping and then we update to maximum L. That's our approach, right? Li equals to f of 0, Ri equals to f of 1, idx equals to f of 2. So now what? So now this has been popped. So what we will update L equals to maximum of I'm trying to see, like, we are trying to remove 1, 1, 1, right? We are trying to brute force all of them. So brute forcing all of them will say at least there is one thing that has been removed. So removing things is fine enough. I was trying to see, should we care about everything not removed? Should we care about that one? But we have proved that at least one will be removed. At least one will be before this one, right? We have proved, shown that in optimal. Uh, so I think we can go ahead. So because this is our new line now, okay? After this thing has been removed. What about RI? You have to update max R of that one. You have to update of IDX. So what do we do? S dot erase of S dot find of max R of IDX. You remove, oops, you remove this shit. You update that shit to RI because that will be the maximum. You insert that shit back. Okay. And then answer equals to maximum of answer comma minimum of, so or optimal now, or min equals to star of s dot begin of, because among all these r's you have to take the minimum r. Okay, we are brute forcing here. There is no logic. See, if r min is smaller than that, that will be negative, and answer is 0, so it will be 0. What the fuck is this? Why is it an s or no? What is this problem? This is some other contest, bad luck contest actually. So both of them has passed. Let's just submit it and then just see what happens. See, some of you people might have seen this and then you might have gone sad by seeing that there are no good enough test cases. You might have seen the test case itself and like, oh, there are no test cases, I cannot solve this now. Wrong answer on test 5. What can I do? Solution is simple. Solution is clear. I'll just check that out now. Output is 0, but the answer is 38, it seems. How can this be wrong? In this, there is no k. And when k is 0, what am I doing? So k can be 0. If k is 0, just push this one. So that's I think that's happening out of index. It happened like out of bound, and then it went wrong. I thought of seeing if k can be 0 or not. So if k is 0, if k is not 0, we don't do that, and it works. So now it's showing 38. So it was an out of bounds error. So yes, it's just getting accepted easily. See, when I say solutions are simple, implementations are simple, you guys have to believe that. How did I implement this one? Once the solution was clear to me, I just formed some greens which are just splitting them apart. And then for all those greens, just keep removing greens before that. It's like a simple problem, I guess. Like it's not too difficult, right? I'm leaving. I'm not doing anymore. Yeah. What do you mean self-classing? That's enough, guys. I'll be leaving. Sorry, Yatri from corporate Bharat. Have to leave. So you cannot just say please. You have to think about the other person too, okay? So try to understand this problem well, because the ideas that I have used here will be used in other problems too. Because it was same brute forcing idea. Can you brute force one thing? See, you know that green is a rectangle. Can you brute force this? Is what you have to think. Like, can I brute force this one? Okay, if I have to brute force this one, what happens? If I have to brute force this line, if I look at one layer, how to get, if this is the layer, how to get this maximum? Everything that can be moved before that move, because otherwise keeping them here will only affect this length from here, right? So if anything that can be moved forward, just move them this side. Now push everything that side. So this is giving you this optimal greens, and also this green can go behind and touch one green start. So like you have these optimal greens, those are the things that matter. And you're brute forcing on this one, exactly, you're brute forcing on this one, so it's just brute forcing. You have these optimal greens, you're brute forcing, and everything less than or equals to that. For in each layer you have to take maximum. So there you have to be careful. You cannot just do things randomly. That's why I'm maintaining one array that gives per layer. Per layer what's the maximum are for things that are less than or equals to this shit. And after that, thought you were too good for me, my dear. I was listening some other song. This one. Well, you look like yourself, but you're somebody. I'm not getting now, but I was doing better before. Like, so guys, we got one AC. I'm ending the stream. Bye. See you later. Maybe I'll stream tomorrow. If you guys, I may stream tomorrow evening. By then, like the video. See, if I don't get more likes, I'll just stop streaming. Like, if I'm getting views or likes, that can motivate me to do this shit, right? See, I cannot give hints now. It's not that it's not that difficult. You can just, it's not that difficult. Not It's not that necessary. Take it light. It's not that necessary. That doesn't work. Bye, everyone. I'm leaving Pranav Verma. I'll go to gym now. I'm having muscles inside. I'm just hiding them. I'm just hiding them so you guys don't get intimidated. Okay? I reduced my rating so that you guys don't get intimidated by an international master. Okay? Well, you look like yourself.